And hello, happy Monday. Mr. McSparron said that there were some questions about problem number 3 from the free response notebook. I thought we'd go over that. If you read the problem, it tells us we're going to be dealing with chlorides of lead and silver. And the first part, A, is really more about silver, but I went ahead and wrote both equations. Silver chloride dissociating to the silver ion and chloride ion, and lead chloride dissociating to lead 2 ion and 2 chloride ions. Then part A asks us to write the equation. So we've already done that. I went ahead and rewrote it again here in part A. Silver chloride solid at equilibrium with silver ion and chloride ion. Part B asks us to calculate the solubility. Now, when we say solubility, what we mean is, excuse me, not part B, but part A2, AII. When we say solubility, what we mean is the number of moles per liter of the solid that you can dissolve in some given amount of water. And they gave us solubility in moles per liter, which effectively is molar, right? In the problem, they told us that we could dissolve 8.9 10 to the negative 5th grams of silver chloride per 100 milliliters of water. So that is the solubility, but we're going to change it from a mass solubility to a molar solubility because we want to know how many moles per liter. So we'll take the 8.9 10 to the negative 5th grams divided by 0.1 liters. Now we have grams per liter. We'll multiply that times 1 mole per the molar mass of silver chloride. So 107.87 grams per mole for silver and 45 grams per mole for chloride, and we get 6.21 10 to the negative 6 molar, or moles per liter, for the solubility. And then finally in part AII, they ask us to calculate the value for the solubility product constant, the KSP, for the silver chloride. So in order to do this, our first step is to write the equilibrium constant expression for the dissociation of sodium chloride, or the KSP expression, which I wrote the KSP equal to silver plus 1 ion times chloride plus 1 ion. And since in part II we found out that the molar solubility was 6.21 10 to the negative 6 moles per liter of silver chloride, that would give us the same number of moles per liter of silver and chloride. So the value for the KSP is going to be 6.21 10 to the negative 6 squared, or the concentration of silver ion times the concentration of chloride ion. And we got a KSP answer of 3.86 10 to the negative 11 for the KSP of silver chloride at 10 degrees Celsius. Notice they always give you the temperature because KSP values are temperature dependent. Okay, so now we're ready to move on to part B on question number 3, and we're moving to the lead chloride. Now notice here it's a different temperature, 25 degrees Celsius, and they gave us the KSP for lead, 1.6 10 to the negative 5th, and they also gave us the KSP for the silver chloride, which is 1.8 10 to the negative 10th, it looks like. Yes. Now notice this is at a different temperature, 25 degrees. Also notice that the KSP for the silver is much, much smaller for the silver chloride than the KSP for the lead chloride. What that tells us is that the lead chloride is more soluble. You can dissolve more lead chloride in the same amount of water than you could silver chloride. That's an important observation to make, and it will come back. We'll need to recognize that a little bit later in part III. But first, part I, they're giving us two solutions. One is sodium chloride and one is lead nitrate. Again here, the sodium of the sodium chloride is used because group 1 metals are extremely soluble, so we can assume that if we add some amount of sodium chloride, all of the chloride dissolves into solution. And the same with the nitrate for an anion, lead nitrate. If we add lead nitrate, all of the nitrate will ionize, so all of the lead will also ionize. So if we add a certain number of moles per liter of lead nitrate, we'll get all those moles per liter of lead. In this case, we had 60 milliliters of 0.04 molar sodium chloride, 60 milliliters of 0.03 molar lead nitrate, still at 25 degrees, and the question is, will it precipitate? For it to precipitate, the amounts of chloride ion and lead ion, when multiplied together, raised to their coefficients, needs to be larger than the KSP for it to precipitate. If it's larger, it will. If it's smaller, it won't. So what we have done on problem I is turn the volume and the molarity of each of those things, the sodium chloride and the lead nitrate, into moles, and then into moles per liter of the ion. So sodium chloride 0.06 liters times 0.04 moles per liter, right, the molar, is 0.0024 moles, and we divided that by 0.12 liters because we had two volumes of 60 milliliters, so a total volume of 120 milliliters or 0.12 liters. And now that's moles per liter of chloride ion, and it's 0.02 molar chloride ion. I didn't make the change here on the paper, but in sodium chloride there's one chloride for every one sodium chloride. We did the same thing for lead nitrate, 0.06 liters of lead times 0.03 moles per liter for the molarity is 0.0018 moles of lead divided by 0.120 liters again because of the 260 milliliter volumes, and we have 0.015 molar lead 2+ ion. So now if we take those two concentrations of chloride ions and lead ions that are floating around in solution now, right, this is what's been dissolved, we want to see, is this enough to saturate the solution? Will this equal to the total amount of ions that can be dissolved, or is there still space for more ions? If it's enough, the excess has to precipitate. If it's not enough, it will not precipitate. So what we're really finding here is a Q instead of a K, right? Remember, Q is solved the same way as any K, except it doesn't necessarily have to be at equilibrium. It might be, but it doesn't have to be. So when we solve for Q, 0.15, which was the molarity of the lead 2 ion, times 0.020 squared, which was the molarity of the chloride. Now we squared it because there's 2 chlorides for every 1 lead, so raised to the coefficient. I ended up with 6.0 10 to the negative 6th. 6.0 10 to the negative 6th is less than 1.6 10 to the negative 5th, which is the KSP that we got at the beginning of the problem. So therefore there is not as much dissolved ions as this solution could hold. So it's not saturated and it will not precipitate. Okay, and now it looks like we're ready for part II. And the question asks us to calculate the equilibrium value of lead 2 ion in 1 liter of saturated lead 2 chloride solution to which 0.250 moles of sodium chloride has been added. Assume no volume change. Now, okay, we're going to assume no volume change. We just drop some solid sodium chloride in, and it's going to dissolve. This is called the common ion effect. It's a common ion because there's already chloride in solution, and we're going to add more chloride with the sodium chloride. Now, this part of the problem has a few extra steps. It would take a while to get to the answer on this, but what we have to think about here is we're starting with a solution that already has a saturated amount of lead ions and chloride ions. So we're going to start by figuring out, well, how much is that? How much lead and how much chloride in a saturated lead chloride solution at 25 degrees? Well, we know the KSP for that, which was 1.6 times 10 to the negative fifth. If we know the KSP and we know the equilibrium expression, which is KSP equal to lead 2 plus ion times chloride ion squared, concentration of squared, then we can plug in. And the trick here is that for every one lead 2 plus ion, we have 2 chloride ions. So we could think of it in terms of however much, if we say the amount of lead we have is X, then the amount of chlorine we have is 2X. So when we look at the equilibrium expression, it becomes 1.6 10 to the negative fifth equal to X times 2X squared. And I know it feels like you're doubling here, like you're double dipping or something. We doubled the number of X's and we squared it, but you have twice as much concentration of X and we square it. So X times 2X squared is 4X cubed, and we can break that down a little bit and we find out that X becomes 1.59 times 10 to the negative second. Now, the X in this case is the concentration of lead ions, right? And remember that we get 2 chlorides for every X, so the chloride concentration is 2 times that, so 3.17 10 to the negative second. And we're going to make an ice table, but remember now, it started as a saturated solution. We're going to add the solid salt, and then we're going to have the change. So the initial isn't really saturated. The initial is saturated plus the addition of the chloride from the salt. So we have in our ice table, initial for the solid we ignore, but for the lead 2, 1.59 10 to the negative second. For the chloride, 3.17 10 to the negative second plus 2.5 10 to the negative first. That's the ions of chloride added from the solid sodium chloride. Now, from this point, we can say, well, what's going to happen next? We know that we have more chloride ions and lead ions in solution now than there should be, because we started off when it was saturated with as much as there should be. So we know we're going to need to lose some lead and lose some chloride. Really, we want to lose chloride, but in order to get rid of chloride, we also have to get rid of lead. And remember again that for every one piece of lead, we lose 2 pieces of chloride. And what this will show us is that once we get to equilibrium, once the change has occurred, the equilibrium constant, the KSP, has to be the same. So the KSP again will be 1.6 10 to the negative fifth, and the equilibrium value for the lead will be its original value minus some change, which is X. And for chloride will be its original value minus some change, which is 2X. Right? So we can plug that into our calculators with the X and the 2X. If you want, you could solve this with a quadratic equation. I would probably just put it in my calculator and graph it, which is what I did. And when I graphed it, X came out to be 0.0156. Notice that that's very, very close to the original value, right? So we're almost using up all of that original lead by adding extra chlorine. We're taking almost all of the lead out of solution. So the new concentration of the lead, which is what the original question was, would be the original concentration minus that X, minus that change. And the change was, the value would be 3.0 10 to the negative fourth moles per liter. So it's a much smaller amount, right? If you were needing to clean a heavy metal like lead out of a water supply, adding chlorine would precipitate the lead out. Notice it doesn't precipitate all of the lead, but it would precipitate a lot of the lead and possibly precipitate it down to an acceptable level. Okay, and we are on to our final problem. Part III. And this is one that I think at first glance may seem very difficult, but if you think it out first, it's really not as complicated as it seems. This is the one where at the beginning of part 3 I mentioned that the lead chloride was much more soluble than the silver chloride. This is kind of what we're going to ask here. So the question asks us if a 1 molar sodium chloride solution is slowly added to a beaker containing both 1.2 molar silver nitrate and 0.15 molar lead nitrate at 25 degrees, which will precipitate first, silver chloride or lead chloride. Now, without any calculations, the silver chloride is a really good guess just because its solubility was so much lower. It was a magnitude of 5 lower, wasn't it? It was 10 to the negative 5th in the lead and 10 to the negative 10th in the silver chlorides. So that's a good guess, but they want us not only to guess but show calculations. So what I'm showing for the calculations here is, let's just assume that we have a 1 liter container and that we are adding sodium chloride, so essentially adding chloride ions. And we're going to say, well, if I have, for the silver, 0.12 moles per liter of silver, how many moles per liter of chloride would I need to reach my KSP at 25 degrees for silver chloride? And then the same thing for the lead. If I have 0.150 moles per liter of lead, how many moles per liter rather of chloride ion would I need to reach my KSP? Now, the trick though is in the lead chloride, remember that it's not concentration of lead times concentration of chloride. It's concentration of lead times concentration of chloride squared, right? We have to have that 2 on there. And remember that for each lead ion we need 2 chloride ions, so it's squared and it's 2x. So when we solve for the KSP of lead chloride, well, we're solving for the amount of chlorine actually, 1.6 to the negative 5th times, or is rather equal to 0.150 times 2x squared, we end up with x equal to 0.0516 and 2x equal to 0.0103 molar chloride ion. Now that is a much larger number or amount of chloride ions than was required to make the silver precipitate. We only needed 1.5, 10 to the negative 9th moles per liter of chloride ions to precipitate the silver. So, as we thought in the first place, because silver has so much lower of a solubility than lead does, the silver chloride will precipitate long before the lead does. So the answer is silver chloride first.